Good afternoon. I will present generating multivariate time series with common source coordinate, written by Jean-François Alinsiev and was part of the conference NeurIPS in 2022. The model is interested in generating synthetic multivariate time series, which preserve utility and statistical properties. It also preserves the relationships between the channels and features, and it preserves the quality of time series and the relationships between time series. What is a GAN? A GAN is composed by a generator which inputs noise, and its job is to create fake samples. The discriminator, which input is real and fake data, and its job is to classify if it's real or false. The discriminator is trained to maximize the probability of assigning correct labels. At the same time, the generator is trained to minimize this term here. It wants to create the newer distribution as the real data as it could. The objective is to propose a novel framework that takes time series common origin into account and favors channel features relationship preservation. The global objective is composed by a local objective, which wants to minimize the distance of the probability distribution of a channel of real data and synthetic data. The central objective is to minimize the distance between the conditional distribution taking into account a channel and the other channels. As the noise inputs is shared by all the generators, it can be seen as the second equation. Here we can see the noise that is shared by all the generators. And each generator has a discriminator. It's composed by 1 to C channels. Each channel represents time series. The input of the central discriminator is the concatenated channels and also the real data. Synthetic signals are concatenated and used in addition with real data as gradient ascent in the central alpha. The discriminator in the end, we take gradient descent on generator parameter theta. So it can be seen like a three-game player with min, max, max. The central discriminator is composed by three multi-layer perceptron. Inside each one has a liner, leaky, residue, and dropout. In the part of the experiment, three datasets were simulated. The first one was derived with this formula. Each one has two patients and two signals, so 2 time series. The second one is the same as the first one, but the frequency is multiplicated in the middle. And the third one, Gaussian noise, is injected. It was evaluated with diversity and correlation. In the diversity, it was observed that the two patients were synthesized, and the metric used was Western distance. In the correlation analysis, they verified the amplitude of channel 1 and channel 2, that they were similar. We could see that without central discriminator, it performs worse than with central discriminator. Also, that there is a trade-off because when there is good correlation, maintaining the diversity does not. Catch 22 was used which is a method to infer small sets of time series features. We could see here that it is correlated. This is the synthetic data, a correlation matrix with central discriminator. And without, we could see that it does not take the correlation in account when you generate. A second experiment was taken in account the dataset I-state dataset classification task. It's composed by 40 channels and the target variable is 0 or 1 if it blinked. It's a classification task. It was trained on real data and tested on fake, and trained on fake and tested on real. We can see that it performed well, better with central discriminator. Also, there was considered a base model, which was a LSTM, followed by a liner and a sigma. The experiment was 80% of the real data was used to train the classifier. No, it's used to train the GANs. And the synthetic data was used to train the classifier, and it was evaluated on 20% of the real data. In the green, we can see the cosigan and how the channel increment also the accuracy in the classification task. And the inverse happens with the baseline. Also, we can see that it does worse than the baseline in channel 2. The state-of-art methods. It was compared with TimeGAN, Fourier, and we could see that it outperformed these methods in the classification tasks. For diversity, the data was plotted in 2 axes, and it was observed how the synthetic data, which is the blue, covered the red, and we can see it has a better, it follows the distribution more accurately with cosigan. In conclusion, cosigan was presented as framework for multivariate time series generations that is able to preserve correlation between the channels. It is able to generate time series that are more similar to real time series and achieve better performance in classification tasks compared to other methods. Cosigan can be parallelizable and it is not competitive for 2 channels. In future works, it could be extended for practical cases when channels correspond to different time series, for example, temperature, respiration, and heartbeats. Limitations. But privacy is not addressed in the article and is an important characteristic in synthetic data. In the domain of medical healthcare, which is the domain that's the classification data sets that they used. And it was only tested with 1 real dataset and low dimensional time series. Thank you.